single variable functions. And what I'm going to do is I'm going to run a parallel to that. So as you know, the first thing we do is look for what are called critical points. Okay, and what are critical points? Well, critical points are where or turning points are where the function, the derivative of the function becomes zero. Okay, so so those particular variables, the derivative is zero because something's going to change. Either before that the function is increasing and then becomes zero and then it decreases, or it decreases and then increases, or it could be just point of inflection in 1D. Now, in any case, it's an important point because it's as you know, it's also referred to as a stationary point. Okay, where some change is about to happen. Now, in the case of multivariate functions, the critical values are calculated in a similar way, is by calculating the first derivative. So the procedure is, what we want to do first is we want to calculate fx and fy. Okay, this is for functions of xy, for instance. Now it'll work for functions of xy and z as well. Okay, but here we're looking at just functions of xy. So first thing you do is you calculate fx and fy, and once you've got fx and fy, equate to zero. Equate to zero. In other words, you're looking at fx equals 0 and fy equals 0. Now you find the values of xy. Okay, find xy that satisfies both simultaneously. Satisfies both meaning this fx equals 0 and fy equals 0 and fx equals 0 simultaneously. Okay, so that's your first aim. Once you find those values, let's say the pair is AB. So you found a pair of values AB, so fx AB is equal to 0 and fy AB is equal to 0. Then what you do is you do what's called a second derivative test, similar to 1D. Except in this case, the second derivative test is a slightly more complicated because it will involve both derivatives. So how it works is as follows. You calculate what is sometimes referred to as the Hessian, okay? And we call this D, and D is basically, it can be written as it's a nice and easy way to remember it. It can be written as a determinant. So fxx, okay, fxy the mixed, then fyx and fyy, which means it's actually just fxx fyy minus fxy squared, as long as the what's it called? The function f is continuous, of course. So that's an assumption in any case in all our analysis here, is that function f is continuous. If it's discontinuous, of course, you have to break it up into piecewise continuous pieces and then study each piece separately and find local maxima or minima there. But anyway, that's not what we're going to be doing. We're looking at straightforward, nice functions that are continuous everywhere, or at least continuous in the domain of interest. Anyhow, let's continue. So once you find this D, then it becomes more an if-then statement. So we have a bunch of conditions that we want to look at. First thing is that if DAB, okay, so that's the Hessian just above, calculated at the point, the critical value AB is greater than 0, and if the second derivative at AB of x with respect to x is also greater than 0, then we say that f at AB is a local minimum, and AB is where the local minimum occurs. Similarly, next condition is, again, if DAB is greater than 0 and fxx at AB is less than 0, then FAB is a local maximum. Okay? Okay, so third condition is if DAB is less than 0, then FAB is neither a maximum nor a minimum. It's in fact called a saddle point. It's called a saddle point. Of course, the saddle as you can see here. So it's called a saddle point. Now, so the reason it's called the saddle point, as you can see here, this is an actual picture of it. See the similarity? It's quite similar. Here, see how this is and this way. Okay, so here you'll see similar in this picture here. So you see there's your saddle point. So it's neither, here looks like a minimum, but on this side it looks like a maximum. So it's neither the 2 points. So it's called a saddle point. And as you can see, it looks very similar to an actual saddle. All right, let's move on. So first step here would be to calculate, of course, fx and fy. So fx in this case turns out to be clearly 4x cubed, okay, minus 4y, okay, and we will equate that to 0. And fy turns out to be, of course, 4y cubed, okay, minus 4x, and equate that to 0 as well. So now what we want to do is solve these two equations simultaneously. So the one thing we could do very quickly is clearly we can see that from this one here, y is equal to x cubed, okay, and from this one we can see that x is equal to y cubed, okay. So by substituting this into this equation, we end up with x is equal to, so instead of y we're going to put this, so it's going to be x to the 9. So it's cube of cube. This implies we end up with x9 minus x equals 0. Okay, and this further means that that we take the x common, gives us x8 minus 1 equals 0. This implies that this can be further factorized, so it's going to be x4 plus 1 into x4 minus 1 equals 0, which further implies we can further factorize that into x squared plus 1 into x squared minus 1 equals 0, which can be further factorized. This should be the final one. So we end up with x plus 1, x minus 1 equals 0. Now, of course, this only gives you complex roots. This gives you complex roots. So the only three, that's this one, and this one, gives us real roots. So we get x is equal to 0, x is equal to 1, and x is equal to minus 1. So we get three values of x, and these three values of x give us three values of y. So this implies y is equal to 0, this implies y is equal to 1, and this implies y is equal to minus 1. So our three critical values are 0, 0, okay, 1, 1, and minus 1, minus 1. These are our critical values, okay? So we have now completed the first step, which is to find our critical values. Now the next step, of course, is to calculate, let me go back here for a second. There you see, we need this d. Okay, let's calculate that. So we have fxx now is equal to 12x squared. Fyy is equal to 12y squared. And fxy is equal to minus 4. Okay, it's equal to minus 4. So now, therefore, our d of xy, Hessian, turns out to be 12x squared into 12y squared minus 4 squared. So that's equal to 144 x squared y squared minus 16. So d of, let's now test. Let's test 0, 0. So d of 0, 0 is equal to minus 16, which is less than 0. Less than 0, let's just quickly look at our Here it is. Okay, so less than 0 means that this is an saddle point. So therefore, our conclusion is that therefore 0, 0, f of 0, 0, rather I should say f of 0, 0 in this case is equal to 1 is a saddle point. Okay, so that's 1 point classified and identified. Next, we'll look at d of 1, 1. So d of 1, 1 turns out to be 144 minus 16, and that's equal to 128, which is greater than 0. That's the more important thing, is it's greater than 0. Now, if it's greater than 0, we need fxx. So fxx at 1, 1 is equal to 12. Okay, so that's greater than 0. That's greater than 0. This implies that f of 1, 1, which is equal to, remember it has to go back into the original function, so it's going to be 1 plus 1 minus 4 plus 1, so it's equal to minus 1. Okay, so that is greater than 0. So let's just have a quick look again at our criteria. There's our criteria. There you can see that we have DAB, D11 is greater than 0, and FXX is greater than 0. So FXX is greater than 0 means FAB is a local minimum. So this means that our point here is a, therefore local minimum. It's a local min. Let's test our last value now. So d of minus 1 minus 1. d of minus 1 minus 1 is equal to the same thing. 144 minus 16 equals 128 greater than 0. Let's calculate fxx at minus 1 minus 1, and that's equal to minus 1 minus 1. So that's fxx at minus 1. It's going to be 12, which is greater than 0. That implies that f of minus 1 minus 1, which is equal to, in this case, well, it's going to be 1 plus 1 minus 4 plus 1, so it's also equal to minus 1, is again a local minimum. So you have two local minima here, one at 1, 1, one at minus 1 minus 1, and the third point is a point of is a saddle point. So we've identified all 3 points. So we know the maximum value of the function. Well, sorry, it doesn't have a local maximum. It has a local minimum point, and the local minimum is as here. So let me put these little red around these. So there is your local minimum, one of them. Here's another local minimum. Okay, and the first point we looked at, 0, 0, 0, 0 is a saddle point. So those are our 3 results. So that's it. Thank you. So here's another example. A rectangular box is to be made from 12 meters square of tinfoil. The box does not have a lid. Find the maximum volume of such a box. All right. So let's work with this. So here's our rectangular box, and so let's say it's not supposed to have a lid for the sake of argument. So let's say this is your x along here, y along here, and this is, say, z. So we have our 3 dimensions. Now the volume, let's say v, which is a function of x, y, z, is of course x, y, z. Now it's not supposed to have a lid, so let's say that means the top of it, it's not supposed to have a lid. So this means that we'll have 1, and of course there's this other side here. You cannot see, neither can I. Okay, so let's say that. So you've got 1, 2, 3, 4, 5. So you've got 5 sides. So that means the bottom side, you'll have one of those. So there's x, y. Plus you've got 2 of these sides. Okay, so this side and this side. There's 2 of those, and that's dimension is yz. So we'll say plus 2yz. And then you've got this side here, okay, and the opposite side there. and its dimensions are xz, so there's 2 of xz. Okay, and the xy, as I've told you, is the bottom here and the top, and there's no lid, so there's only one of those. And all of that should end up being equal to, okay, 12, because you've got 12 meter squares of tinfoil. So now these are our two equations, and we want to actually solve this problem. The way this will work is as follows. You need to combine the two equations. So what you do is, for instance, from this equation, okay, we're going to take out z. All right? So it means we have z is equal to 12 minus xy divided by 2 into x plus y. Okay? Okay, so that's your value of z. Now, this implies that v, once you substitute it in there, it means you're going to get xy into 12 minus xy all over 2 into x plus y. Now, let's start by calculating our vx and our vy. So vx, let's say, actually, let's just open this up and write it as 12 xy minus x squared y squared over 2 into x plus y. It just makes things a little bit clearer. So now as we take the x derivative, we end up with 12y minus y minus 2xy squared, okay, and that will be multiplied by, of course, 2 into x plus y, the denominator, because remember, you're going to use the quotient rule, minus the derivative of 2 times x plus y, the x derivative is just 2, so it's going to be 2 into 12xy minus x squared y squared, okay, and that's all divided by 4 into x plus y all squared. Okay, so that's what we get. So this is equal to, okay, all divided by 4 times x plus y squared. Now you will notice that some of these things will cancel. For instance, this 24xy and this 24xy, they will cancel, and these two will give us just 2x squared y squared, and as you take the common outside, you'll end up with, after simplifying, we should get y squared into 12 minus 2xy, okay, minus x squared all over 2 into x plus y squared. Okay, so in a similar way, we'll get vy is going to be similarly done. So once you simplify that, it will turn out to be x squared into 12 minus 2xy minus y squared all over 2 into x plus y squared. Okay, so those will be our two equations. So that's your vx here, and that's your vy. Now from these two, when we equate these to 0, remember, you have to equate these to 0, and then we have to solve for x and y. So we'll end up with 12 minus 2xy, okay, minus x squared equals 0, and we'll have with it 12 minus 2xy minus y squared equals 0. Okay, so this tells us that if you look at this, so if we combine these two, which means if we subtract these two equations, it tells us that x squared is equal to y squared, which implies that x is equal to y. So x is equal to y. Now the reason I'm ignoring the negative ones, because I know you're thinking, what about plus or minus y? Remember, x and y and z are all dimensions, so they can't be negative. So we're ignoring the negative part. So we're only looking at the positive side here. So x is equal to y. So if we put x equal to y in either equation, in other words, in this one or in this one, we end up with x is equal to y, remember. Okay, so we'll end up with, say for instance this one here, let's substitute in this one here, so we get 12 minus, and we'll substitute y equals x. It's going to give you 2x squared minus x squared equals 0. So now that means this implies that we have 3x squared, so 4. So x is equal to plus or minus 2. X is equal to 2, of course, we'll keep it. Ignore minus 2. Okay, ignore minus 2. Here we've ignored minus negatives. Okay, because we're looking at dimensions. So plus or minus y and plus or minus x and minus y are both ignored. So anyway, so x is equal to 2, and of course x is equal to 2 means y is equal to 2. So we've got our dimensions. This seems to be the only value. We get only one value out of this. Okay, and if these two are 2, that means that in our original here, this relationship which defines z, let's substitute it in there. Okay, let's substitute it in there. So x equal to y equals 2 means that z will turn out to be 12 minus 4 divided by 2 into 4. So it's 12 minus 4 is 8 over 8 is 1. So that means we have 2, 2, 1. That's our own, these would be the dimensions of the box that will maximize the volume. Now in this case you don't need to go any further because this is the only critical value. It has to be the one that maximizes the dimensions of the box, the lidless box. Alright, so that's it. So we've done a practical example of actually finding the maximum volume of a box. Alright.